So today I'm going to talk about a new kind of dissimilarity measure that is looking like and generalizing the ordinary Bregman divergence. And the name of that divergence is called Bregman chord divergence. So it will become very clear with a figure very soon. Just let me know if you have any question during the talk. And this is a joint work with my collaborator, Richard Nock. So as you know, Bregman divergences, they have been presented in the operations research community in the 1960s. So usually the 1967 reference in English is given, but Bregman himself published in Russian before, and actually you can find trace of that Bregman divergence in 1965. And this is a snapshot of the English paper, 1967, and you can see that this formula that we will discuss from now on is called a Bregman divergence and has been mainly used for projection algorithm for finding a point in the intersection of n convex bodies by projection, by what he called at that time deep projection for Bregman deep projection. So Bregman divergence is now very well known and very useful in information sciences. It can be used in information theory or in machine learning and various areas. And the way to look at it is that you take a convex function that you call it the Bregman generator f, and you plot this function here. So I will have a parameter space theta, and then I will have the plot of that function. It's a convex function. So basically, if I look at the epigraph, it's a convex object, and it's smooth and strictly convex. And you measure basically the Bregman divergence between two parameters, θ1 to θ2, as follows. You take the ordinate at θ1, and then you take the tangent line that passes through the point at θ2, and you measure the value of the y value for parameter θ2 at the tangent line, and you take this vertical gap here as a Bregman divergence. So because it is strictly convex, it can be 0 if and only if θ1 equals to θ2. Eventually, you can generalize Bregman divergence by not requiring to be differentiable, and then you need to have subgradient instead of this gradient here. And this has been generalized to matrices or to functions with Fréchet derivative and so forth. So it's really widely popular, and it's gaining more and more popularity in machine learning, as I told you. So one drawback from the viewpoint of experiments and in practice is that you need to compute the gradient here, and sometimes it can be very tricky depending on the generator. And another drawback in application is that if you want to tune here, because you need to tune some kind of functional generator, it's not that easy. So what we will see is one way to make a new family of distances where we can adjust the generator by scalars. And scalars, you can think it of some kind of buttons that you just adjust, and it's much easier than choosing a function in a parameter in a functional space. Okay, this is an overview of interpreting this formulae. This is the same formulae as before, the Bregman divergence here. But here what I do is I take the tangent line that passes through the point at θ2, and I take a translate of that line that passes through θ1, and I still have here at any place the vertical gap, the vertical ordinate, as the Bregman divergence. That's another visualization of what the divergence is about. And it has been widely used in machine learning, as I told you, because also there's some kind of properties, and actually those properties are exhaustive properties for specific classes of distances. So if you take clustering, what you know is that if you cluster on the right-hand side for the Bregman divergence, so if you want to minimize the Bregman center C, the centroid, that minimize this, then you will find that it is the center of mass. And this is here the discrete version, and it is independent of the generator. And moreover, you can show that any divergence that satisfies this property is a Bregman divergence. Okay, and you have some kind of very mild restrictions, but it has been really worked out in 2005 by Banerjee and his co-authors. So Bregman divergence also is very attractive from the viewpoint of information geometry, because if we take a divergence, a smooth distance arbitrary, we can always compute an information geometric structure by taking second and third order derivative for making the dual connections and the metric. And in the case of a Bregman divergence, what you will find is that the Riemannian metric here is a Hessian, okay? And you will find that in the first coordinate system, you will find that the affine connection coefficients are 0. So this means that it is a flat connection. And if you take the Legendre function transformation, you will get a dual potential function or dual Bregman generator, F star here. It's again convex and a proper generator. And for the dual coordinate eta, you will find that the dual Riemannian metric G star here is again the Hessian of the dual potential function, and that the associated connection, affine connection, is also flat because in the eta coordinate system it's 0, right? And we have one more thing here, is that we have the product of the Hessians matrices for parameterized by theta, and eta is the identity, and this is what has been called a Kruse identity. It means just that the basis vector are mutually orthogonal. This is a geometric interpretation. So this kind of thing is also very well studied as a Hessian structure because the metric can be derived from a Hessian of a potential function. Okay? And what's really strong is that whenever you have a dually flat space, you can show that you can always have a canonical Bregman divergence, okay? Which is not the case if the space is not dually flat. So dually flat spaces and Bregman manifold, for example, you can make it synonyms because you have a one-to-one matching. Okay, another thing is that there's a very strong relationship between Bregman divergence and natural exponential families, which are probability distribution. And we had a very nice talk this morning, I think this afternoon or this morning? This afternoon, early afternoon, on representation learning, representation theory, and exponential family. So this is the canonical decomposition of an exponential family, and the function f here, which is rewritten as this thing, as a log Laplace transform, is a strictly convex and differentiable function. So it can be a Bregman generator. And actually, what you know is that if you take two distributions and you take the Kullback-Leiber divergence, then you will find it is a Bregman divergence. Actually, it's a reverse Bregman divergence, but we like to write it as a Bregman divergence with swap parameters. But it will be better here to put a reverse operator. And it is also equal to the dual Bregman divergence and the dual parameterization for swap parameters. And it is also equal to this thing that has been called before canonical divergence in the early days of information geometry, but that we can now rename as a Fenchel-Young divergence. So we have basically those four identities. That is a statistical divergence between two distributions of the same exponential family. So here, a difference is that Bregman divergence, they are between the same parameters. So eta or theta parameters, natural parameters or moment parameters, but the Fenchel-Young divergence, which arises from Fenchel-Young inequality, is between mixed parameters, right? So it's a thing. Okay. And there has been also some work by Junzhang and myself independently on generalizing Bregman divergence by this divergence, which is called a Burberry Raw Divergence, and now that can be simplified as a Nielsen divergence. So again, you take the plot of the convex function, and here what you will take is the midpoint of the parameter, and you will take the ordinate gap between the linear interpolation here and f of the linear interpolation, okay? And if you skew it, not by taking half, but by taking some parameter alpha, and you rescale this Nielsen divergence, then you will find that when you tend to 0 or 1, you will find the Bregman divergence or the reverse Bregman divergence, okay? So it can be easily generalized by this skew family of Nielsen divergences. This is very well known. And of course, because we have, before I show you the connection between exponential families and Kullback-Leiber divergence and Bregman divergence, and because I told you that this guy, Bregman divergence, is a specific asymptotic case of Nielsen divergence, we can find some relationship between the statistical distances here that we can call alpha skew Bhattacharya distance. So we have here a distance, statistical distance between densities that are equivalent to parameter divergence on parameters. Okay, so the key point is that when we design Bregman divergence, we have some kind of geometric design because we plot the function of a convex function and then we measure some kind of gap. So let's try to invent new kind of divergences and try to motivate how to use them. So 1 or 2 years ago, I did this work that was called the Nielsen chord divergence. And the idea was very simple, is that you take two scalar parameters, alpha and beta, and if you have if you want to measure the distance between P and Q, first you take a linear interpolation at alpha, then you take a linear interpolation at beta for alpha and beta in 0, 1. So basically you will fall inside this segment. Then you take the lower chord that is defined by these two interpolated at alpha beta position, and you have again interpolation inside alpha and beta for the upper chord, and you measure this vertical chord gap. Okay, so this is a very simple generalization of Nielsen divergence, and of course, but you can reinterpret. So one way to rewrite it compactly is as follows, but you can also visualize it as a difference between a Nielsen divergence here and a Nielsen divergence here. Okay, so as a difference between two Nielsen divergences. Okay. So let me introduce you the scalar Brahman chord divergence now with scalar parameters, and this is defined as follows. So usual Bregman divergence, as I mentioned, is that you take the tangent line at θ2, and then you take the vertical ordinate with reference to θ1. So what we are going to do here, we are going to play with this tangent line, and we are going to make it a chord. And the way to parameterize the chord will be according to my two parameters, θ1 and θ2, and two scalars, again, alpha and beta. So with alpha and beta between 0 and 1, I will define these points that fall inside the interval θ1, θ2. And then I will make this chord here. And I will take the vertical ordinate gap here as the chord divergence that we will write as BF alpha beta. Okay? And by geometric construction, we have the law of the indeterminables, and we also know that basically our Bregman chord divergence is less or equal than our Bregman divergence. So this is very easy visualization of that property. Okay, now what you do is that instead of writing my Bregman divergence as f θ1 minus the equation of the tangent line, I put the chord equation that I evaluate at θ1 for measuring this blue gap here, and I just plug the formulae that you will compute by simple stuff, and you will find this expression here in the end. So we are in the scalar case, θ1 and θ2 are reals. Okay. So we have some properties, obviously. One is that the symmetry, if we swap alpha and beta, because the chord is the same, is defined as the same chord. And then we have also some generalization when alpha tends to 1 and beta tends to 1. Basically, our chord divergence will tend to the ordinary Bregman divergence. And what we can do also is we can have alpha that tend to beta. And then basically we will take a tangent line in between θ1 and θ2, not taking the tangent line at θ2, but in between θ1 and θ2, and this will be called the tangent Bregman divergence. Okay, so you can have a subfamily of Bregman chord divergence by doing that. So now the interesting case is how to extend it into the multivariate parameters, because this is the case that you are interested in. And the way to do it, one way to do it actually, is to define some classes of convex Bregman convex functionals here as follows. So lambda will be a scalar, and θ1, θ2 will be vectors, and I will basically define this function. Okay, so I have a multivariate, and this becomes a scalar function. Okay, and you can show that this function, of course, at 0 is f θ1 and at 1 is f θ2, and it's also a scalar convex function. So it's a proper Bregman generator, and then you use the form of formulae to define the multivariate Bregman chord divergence as follows. Okay. So now you plug again what we've seen before, and you find this equation here as a formulae for the Bregman chord divergence in the general case. Okay, so this is the drawing, and what we have some kind of software that you can look from the home page where you can play and adjust alpha, beta, and gives you some numbers here for various generators. And I just want to conclude by saying that, of course, what we have been doing here is removing the gradient by having a chord. And this is helpful in machine learning because computing gradients can be very tricky, especially when f is not in closed form solution, and it adds you a double bottleneck problem. And we are currently investigating how to use it. So let me conclude as follows. So Bregman divergences are widely used distortion measures, and it has been implied in many fields of information sciences. Of course, one of the bottlenecks for machine learning is the use of gradients, and the way that you cannot tune the generator very easily. You choose the Shannon negentropy or the Berg negentropy or things like that. Here, what we have is by doing the chord divergence, we have a biparametric family of distances where we just have to tune two scalars, alpha and beta, between 0 and 1. So you can plug it into the optimization or cross-validation to find how your generator is changing. And some properties that are interesting is that our Bregman divergence basically upper bounds this Bregman chord divergence. And as I said many times already before, we don't need to compute the gradient. So just to come back to the history of Bregman divergence, I told you it was in operation research. And the thing is that people wanted to compute a common point in the intersection of n convex bodies. And the way to do it is called a method of alternating projection. So you have a starting point here. You are going to do a projection as a minimization of the distance between this point and the convex body. You take in cyclic order the constraints, like A and B here for two constraints. I project here, and then now this is my new approximation, and now I'm going to project onto the second constraint, and I repeat cyclically. Okay, here I have just two things, and you can show that is going to converge into the intersection, or is going to converge to the minimum distance between your convex bodies, right? So what are the distances, D? What are the D projections that satisfy this kind of convergence property for finding common intersection points? And one sufficient condition is to have Bregman divergence, okay? And as I told you, it was already done in the 65, this kind of thing. Okay. This is, you can find many applications of this alternating projection mechanism for computing the divergence between two submanifolds in information geometry, again as alternating projection. And the question is always when it is unique, this kind of convergence. And what you can show in information geometry is that once some manifold is nabla flat and the other is nabla star flat, then you have convergence and a unique solution to this minimization by the cyclic projection method. Okay, and the software I mentioned for playing for visualization is available at this homepage. Thank you.
So many thanks for the very interesting talk. Are there any questions, comments, remarks?
Is it possible that the Bregman chord divergence is just another type of Bregman divergence?
No, because the way that I define the f is according to my 2 points where I want to evaluate. So at first I thought that maybe it's rewriting a function f into another convex function, but it's not the case. That's because every time you find 2 points, it's going to make according to the relative position of your arguments. So you cannot rewrite. Yeah, the question is that is my Bregman chord divergence a Bregman divergence somehow, right? For no.
So further questions, remarks, comments? Did you study what happens if the dimensions get higher and higher?
No, actually, this is just one very quick idea, to be honest, that we carry out, and now we really need to go into the main stuff of it, and for example, to characterize that class of distance, and for population minimizer or prediction, we are investigating now properties.
Have you considered how it compares to the regular Bregman divergence in terms of preserving the monotonicity? That is to say, if you have theta 1, theta 2 is further from theta, has a certain distance from theta 1, and then you have theta 3 from theta 1 is further. Does the Bregman chord divergence preserve the order? I don't know, there's probably a better way of formulating this.
I understood your question.
Yeah.
It's a very nice question. Actually, I think all cases are possible because somehow what saves us for Bregman divergence, because the order can also be swapped with Euclidean stuff, is that we have a 3-point property or 3-parameter property, right? And this is from these 3 properties that we have a dual Pythagoras theorem when the geodesics are dually orthogonal, right?
Yeah.
The dual geodesics are orthogonal, right?
Yeah.
And so here we need to play and to get some kind of identity between 3 points or 3 parameters and try to interpret it as monotonicity or not, depending on condition. Probably there's some scalar product, and we need to find out stuff, but I think we can do.
Yeah.
So we have not done yet. It's early preliminary result.
Thank you.
Are there further questions, remarks, comments? Okay, if not, let's thank us, Frank, again.